is on polar coordinates. So polar coordinates are kind of strange. So when I was passing the papers out, some of you guys were like, what is this? This is weird. Okay, it doesn't look like a normal grid, right? The grids that you guys are used to are what we call rectangular coordinates because we have like a 10 by 10 grid or something, you know, so it's an x coordinate and a y coordinate. So these are going to have an r coordinate and a theta coordinate, okay? And what this means is from a certain center, you know, so if I'm talking about having a point, and I want to say, oh, I want to go 3 units away, like 3 miles away, in the 45-degree angle direction. Okay, that means that we would need to think about 1 mile, 2 mile, 3 miles, and we would be along that in like the 45-degree angle. Does that make sense? That's what we're going to be doing with polar coordinates. Okay, so polar coordinates allow you to graph these really awesome things. So we have different curves, which we're going to talk about in the next section, which is like a lemniscate, a rose curve, an Archimedes spiral, and so on. Okay, kind of cool, right? That you can graph things like that. So a lot of people are like, well, what's that really going to do for us in like real life? Really, it's useful whenever we're talking about anything that would be going out a certain distance at a strange angle. Okay, so like I just gave you the example of something going out a direction of 45 degrees, right, a certain distance, which we've kind of talked about with planes and boats and so on. Okay, so let's start with the basics. So since every point in the polar coordinate plane is given by r comma theta, where r is the distance from the pole is just another word for origin, and theta is the direction you go towards. Both r and theta can be positive or negative, which can be really confusing at first. So we're going to do several examples of this. So in this example, if we have 5 comma pi over 4, I want you to think about where the pi over 4 line is. Okay, so this is the pi over 4 line. And what we're saying is we're going 5 units along that pi over 4 line. Okay, so think about where that would be. So we have 0 units, 1 unit, 2 units, 3 units, 4 units, 5 units. Is it right along the edge of that? Did you guys see that? It would be right there. That would be that point. You guys see 0 would be right at the pole. 1, 2, 3, 4, 5. All right, so what do we think if we have pi over 6? Right, which is that line, and I say, instead of going 3 units along pi over 6, let's go negative 6, or negative 3 units along pi over 6. Yeah, so Kenzie's pointing in the opposite direction. Does that make sense to go away from it? So it's like this line is continued to the 7 pi over 6 line, right, as you guys know it from the unit circle. So we're continuing in this direction, and we're going to go 3 units. Instead of going this way, we're going to go backwards. We're going to go this way, 1, 2, 3. And that's going to be our point right there. Does that make sense? Do you guys get it? Okay. So we can also have things like 4 comma negative pi. And negative angles, those are the angles that we had before with negative angles. Do you guys remember negative angles? We go clockwise. We go not counterclockwise, we go clockwise. Just like before. So if I talked about like negative 30 degrees, it was like right there. Do you guys remember that? So if I say negative pi, where's it located? It's still at the same place as pi, right? So this would be the negative pi line. And then we're going to go 4 units along that line. So do I go to the left or to the right? Is my point on the left side or the right side of the graph? On the left side. That's where it gets confusing with the negative angles because people are like, oh, now it's going to go backwards. But the r isn't negative, right? R is saying 4, positive 4, along that negative line. So we go 1, 2, 3, 4, and it's right there. You don't have to draw the little swoops. I'm just doing that for your benefit so you can see it. All right, here's the really confusing one. You ready for like the double negative in math? Oh, it's rough. All right, so we're going along the negative 3 pi over 2 line. Right, so everybody visualize where negative 3 pi over 2 is. So start at 0 and go backwards 3 pi over 2. Where am I located? I'm not going down. I'm at the top, right? Because I'm going to go around. Here would be negative pi over 2, negative pi, negative 3 pi over 2, right? Does it make sense? So this was like negative pi over 2, negative pi, negative 3 pi over 2, going around that way. So we're going along this line. Okay, I see. So Kate's putting it together. That's why he was saying it's going down. So now that we have negative 3, we're not going along this line. We're not going 3 units along the line. We're going 3 units in the opposite direction of the line, right? So we're going this way. 1, 2, 3, right there. So some of you are probably like, is it just the same as 3, 3 pi over 2? Maybe, but is that always like that? You gotta be careful. All right, so if I have 0, pi, so where's my pi line? So it's right here. But if I'm only going 0 units along it, yeah, it's gonna be in the origin, or what do we call it in polar coordinates? The pole. It's gonna be at the pole. All right, how about this one? So here's our 0 line. 3 units, 1, 2, 3, it's right there, right? Yeah, so ideally we don't draw these with these little lines. I'm just drawing these to help you. But on your homework you would just draw like that single point. That's what we're doing. Okay? You guys try these 3, see what you got. All right, let's see. So it says -1, -5 pi over 6. So -5 pi over 6 means we're going in this direction around, right? To 5 pi over 6 in the negative direction. So it would be like along this line. Did you guys all have along that line? And then we're going backwards by 1. So we're going to go along this line, really, which will put us right here. Were you guys right there? So you should be right there. You with me? All right, 11 pi over 6. Well, that's going to be this line, right? And we're going 2 units along that line. So that one's not too bad. That's right here. We like that one. We like when they're both positive. All right, and then -3, -pi. Ooh, we got that negative pi thing again. Well, that's still in the same location as pi because it's just going around this way. And we're going -3, so we're going to the right side, not the left side, right? So we're going to go 1, 2, 3. Did you guys get those 3 points? Yay, good. This homework will be very easy for you then. All right, so number 10 says name 4 different polar coordinates that represent the point 3, 5 pi over 6. Okay, so keep your radian measures between -2 pi and 2 pi. I want you to think of all the different ways you can name the angle, all the different radius numbers you can use, and so on. So let's graph 3, 5 pi over 6. It's always hard to do with polar coordinates because here's how we draw our grid. It's not like, you know how like our previous grids were like this? That's Cartesian coordinates or rectangular coordinates. Named after René Descartes, right? Do you guys remember how he came up with that? René Descartes. He was like laying in bed sick and he watched as a fly was flying around on his ceiling. Haven't I told you this story before? No? Okay. So Descartes, do you guys know Descartes? I think therefore I am, that guy. Yeah, how'd you say it again? Descartes, yes. So yeah, he came up with Cartesian coordinate plane. Look at our ceiling. Do you guys see how we have ceiling tiles that form a grid? So he watched as a fly was going, from one place to another place, and he was like, oh, I wonder what distance that fly has traveled. Because that's what we do when we're sick. We look at the ceiling and come up with brilliant math things. All right, so anyway, so ours is going to be the polar coordinates. So it's going to be like this. This is how you draw it. I know it's super hard for you guys to draw these circles, but try. You're a pro at it. So 5 pi over 6 is going to be like 30 degrees away from 180 degrees, right? So it's going to be along that line. And we want to go 3 units along that line. So 1, 2, 3. So it's right there. So are there different ways to represent this? I don't know. What's one way? You can make what negative? The r. Okay, so if r was negative, then we would have to talk about the line that's over here, right? And what angle is this line that's over here? Ah, you guys are good. So it could be 11 pi over 6, or it could be negative pi over 6. I agree. So we could write it as -3, 11 pi over 6, or we could write it as -3, negative pi over 6. Good. Those are the 2 hardest ones. You got them right away. Ah, Kate's good. All right, so he says this could be -7 pi over 6. So he says that we could do +3, -7 pi over 6. And then the fourth one was the 3, 5 pi over 6. Are there any other ways? I think that's it, right? Is that good? Any more? I think that's it. I tricked myself by saying name 4 different polar coordinates, and then I was counting the first one. All right, so number 11, so find the rectangular coordinates that correspond to the following polar coordinates. So let's go backwards. So let's say we have these as our polar coordinates, and let's write it in the xy form, right? So rectangular coordinates means our normal xy coordinates. That's what that means. So as if I had the Cartesian coordinate plane, I'd say, how much do I go to the right? How much do I go up? And so on. Okay, so let's think about it. So if I have 3 comma pi over 4, that means that we would have along the 45-degree angle line, and we go out 3 units. Okay, so we're going to have some point that's over here. We want to know the x coordinate and the y coordinate. Okay. This is why we learned this after vectors, because we did something like this in vectors. Do you guys remember? Yeah, Greta?
Would 3 be the hypotenuse?
Yeah, 3 is the hypotenuse.
Then it's 10.
Well, then you have y and x. So how do I just solve for x, and how do I just solve for y? So we know that this is 45 degrees in here, right? The other one's 45 as well.
Magnitude cosine of the 45 degree magnitude sine.
Yep, good, that's perfect. So we do that. So we do 3 cosine of 45 degrees, comma 3 sine of 45 degrees. And if you remember when we talked about vectors, we did that. We found x by setting up an equation. We said, oh, cosine of 45 degrees is equal to x over 3, right? Adjacent over hypotenuse. And when you multiply the 3 over, that's how you got cosine of 45. All right, so we get that. And we actually know cosine of 45 is root 2 over 2. And sine of 45 is root 2 over 2. So we get 3 root 2 over 2 and 3 root 2 over 2. So those are the rectangular coordinates. I think you're back at that table. Right? We switch things up again. All right, so 5 comma 5 pi over 6. So I don't need to sketch it out. I could actually just say, oh, I'm going to do 5 cosine of 5 pi over 6. 5 sine of 5 pi over 6. All right, and we're going to find those. So 5 pi over 6 is over here. Cosine is going to be, what's the cosine of 5 pi over 6? Some of you guys were having trouble with this on the test. You're forgetting your basics. Yeah, it's negative root 3 over 2. Yep. And then sine of 5 pi over 6 is 1/2. So together we get negative 5 root 3 over 2, comma 5 over 2. All right, you guys try the next 2. It's this one, the notes one. Yeah. Okay, so this next one, if you kind of sketch it out, you can tell what point it's going to be. So if you have 3 comma 3 pi over 2, that should be 3 units along here. So there was some on your, like that on your midterm where you kind of had to figure out, like when you had a vector that was like 5 comma 0. And you had to think, oh, I'm going out 5 and I'm going up 0. And I asked you for the magnitude and the theta. Your magnitude should be 0, and your theta, or sorry, not 0, that should be your theta. Your magnitude should be 5, it's 5 units long. Your theta should be 0 degrees, right? So sometimes it's easier, instead of doing all the like cosine and sine stuff behind it, to just think, oh yeah, where's that going to be located? Can I think of that in my head? So if you see 3 comma 3 pi over 2, you can just say, oh, that's going to be the point 0 comma negative 3. Did you guys get that? It should be 0 comma negative 3. But this next one is pretty hard, right? So we have 10 comma 5.2, and the question is, well, what's 5.2? All right, that's a radian measure. I know it looks like it's already in rectangular form, but it's not. That is some kind of radian measure, because I told you it was in polar form. Okay, and it's not quite at 2 pi. 2 pi would be like 6.28, right? So you don't really need to know where it is, but you can just use the formula where you say, oh, it's just going to be 10 times cosine of whatever 5.2 is, and then it's going to be 10 times sine of whatever 5.2 is. But just make sure that you're in radian mode, not degree mode. A lot of people think when it just says like something like 5.2 that it's degrees. There's no little degree mark that's indicating that, right? So we have to assume that it's in radian mode. Ooh, almost dropped all my stuff there. So make sure your calculator is in radian mode. So I got like 4.685 comma negative 8.835. Did you guys get those numbers? Yes, they're not always nice. So don't think that they're always going to be like those nice unit circle values. Sometimes they're weird ones. Okay, so let's go backwards. So it says find the polar coordinates that correspond to the following rectangular coordinates. So these are in the form x comma y. So do you guys remember that process that we just did there for vectors? It was, we always said like finding the component form, the x and y components is what we would say. So now we're going from like component form and we're going to polar coordinate form, right? We want to know the r and the theta. Okay, so before when we did vectors, I always told you to think about the quadrant. Because remember when we would do like inverse tangent, we'd get like, oh, it's in the fourth quadrant, but it really wasn't in the fourth quadrant. It was actually in the second quadrant or something. We had to like add 180 or subtract 180. Same idea with these. So always think about the quadrant. So if you have 2 comma negative 2, or root 2 comma negative root 2, what quadrant are we in? Yeah, we're in the fourth quadrant, right? And you can kind of tell the degrees already. So if I was asking for degrees or radians, it doesn't matter. If I asked for the degrees, it'd be 315 degrees, right? If I asked for radians, it would be 7 pi over 4. Doesn't matter which one. I don't care. Usually I have you guys use degrees because it's easier for you to visualize. So that's going to be our theta. Our theta is 315 degrees. How do you think I find r, the length of that? Yeah. No, that found a theta. Think how it's related to vectors, guys. So what we're saying is we go out root 2 and we go down root 2, well, negative root 2. Yeah, and we want to find this length, right? So we do a squared plus b squared or x squared plus y squared. You could do under square root. So we're going to do square root of 2 squared plus negative square root of 2 squared, just lots of square roots, equals that. It was the same thing as the magnitude. Right? Magnitude was just the length of a vector, and that's what we're doing. We're finding the magnitude. How far out we go, the radius. And we're going to call that r. So we got r is equal to the square root of 2 plus 2, which is the square root of 4. So my r is equal to 2. So if I write it in the form r comma theta, r is 2, theta is 315 degrees. That's it. All right, 3 comma negative 1. Or root 3. Man, I keep leaving off my roots. So it's like 1.7 something comma negative 1. So somewhere around there. So again, we need to find our theta, and we need to find our r. Okay, this may not be one that you recognize off the top of your head, so let's do our tangent. So if we're trying to find theta, we do tangent of our, tangent of theta equals the y value over the x value. Do you guys remember that? Like one weekend, and you forget everything, huh? You had so much fun at prom, just can't come back and remember all this vector stuff. It's rough. All right, so we do our inverse tangent, and I would just make sure that you're in degree mode, so it's a number that makes more sense to you. And it's going to be a nice number in this case, because what we're saying is tangent of theta equals negative 1 over root 3. Do you guys remember way back when we would like divide by 2, divide by 2? That's saying our sine is in the form of 1/2 and our cosine's in the form of root 3 over 2, and they have to have opposite signs. Okay? And so our calculator is giving us that theta is equal to negative 30 degrees. So that works. We could do negative 30 degrees, and some of you guys did that on your test, and I counted it. So that's fine. Yeah. So you could write it as whatever the magnitude is, comma, negative 30 degrees. Or you could do whatever the magnitude is, comma, 330 degrees. I don't care. Usually I do between 0 and 360. Because those negative angles, as you saw, get a little confusing as you're trying to plot the points, right? All right, so how do we find the magnitude? Yeah, so our magnitude, or our r in this case, is going to be the square root of x squared plus y squared, which is the square root of root 3 squared plus negative 1 squared, which also ends up being 2. Right, so it's going to be 3 plus 1, square root of 4 is 2. So we could write it either way. I didn't give you guys much room for these, did I? All right, here's one that doesn't need much room, because think about it. So if you have 0, negative 7 over 2, or negative 7 root 2. What's our angle? 270. What's our radius? I don't know. What's this length here? 7 root 2, right? So we're going to say 7 root 2, comma, 270 degrees. Does that make sense? It's just a length, so it would be positive. Because you're saying you go in the positive direction towards the 270. So Kate was saying, what about like negative 7 root 2? Could we do a negative 7 root 2? But what would be the angle with it? 90, right? So you could do 90 degrees, but then it'd be like a negative 7 root 2. So it's a little tricky. All right, does this all make sense? So what if you have something like really generic like this next one? I'll put it down here. So if I have negative 3.5, comma, negative 1.2. And it's like, oh, these definitely are not unit circle values. I shouldn't know this off the top of my head. Right, we're just using two formulas. So the formula is that the tangent of theta is equal to y over x, but we have to think about quadrant, whatever quadrant we're in. So let's find theta. So we do tangent of theta equals negative 1.2 over negative 3.5. What quadrant do you think the calculator is going to give you? It's going to give us the first quadrant. You see how those negatives will go away? So it's going to say, oh, tangent's positive. It's going to give us, if you think about inverse tangent, between negative pi over 2 and pi over 2, or between negative 90 degrees and 90 degrees, it's going to give us this one. Is that what we want? No, we want what quadrant? Yeah, we want quadrant 3. Because it's a negative x and then a negative y. So we use our calculator and we're like, okay, inverse tangent of 1.2 over 3.5. I got theta is equal to 18.925 degrees. Right? So how do I adjust it? Add 180. So I get 198.925. Is that in the third quadrant? Yep, a little bit before, a little bit after 180, right? Not quite to 270. So our theta's good. So this was the first formula we use. Our second formula involves r, which previously we called magnitude. Now we're calling it the radius, right? And all that is x squared plus y squared. You can see how everything's interconnected. You're so speedy with your fingers. I can hear all that clicking. What'd you get? It ended up being pretty nice. 3.7. So we use two formulas in these problems. And sometimes we don't need the formula, because sometimes we can just think about where it's located, right? If it's one of those like 0, comma somethings, or 7, comma 0, we can think about that. So our rectangular form is going to be 3.7, comma 198.925 degrees. Okay, got it. Good? All right. What's the last one, right?